Okay, so right, so welcome to this solubility equilibria. This is the last exam standard we're doing. We've done the 3.4 and the 3.5, so we're going to be looking at the 3.61 now. So it's a lot of calculations in this one. So if you're good at maths, you'll be good at the standard. Then there are also some explanations as well. So what we're going to just look at today is starting from the basics, really, from ion solubility rules and so on. So we'll look at those, and then we'll look at the calculating of solubility and calculating Ks. So these are the things you should know from previous levels, so you can tell me how good you are at it or how not. Can you break up an ionic compound into the component ions? Because that's really important. So if I said Ag2CrO4, could you tell me what the ions are? So I see there's a bit of typing there. Andrew, you're correct in that it's a silver ion, but you actually need to put the charge on, because if you just said Ag, I know you're just trying to be quick and so on. Great, so it's Ag plus. Now the chromate part was CrO4. It's quite difficult just me saying it out loud without you seeing it, but it's the chromate, so you need to put the CrO4 2 minus. So that's we'll do some examples of that. Then the solubility rules. You don't need to know them directly. In other words, I won't do examined. Is this soluble or is this not soluble? But by knowing the solubility rules, you know what's going to be precipitating, so you don't get distracted by other things. You know exactly what to focus on in your calculation. So in that way, they're really helpful. Then don't forget your C is equal to NV and your concentration formula and your mass and molar mass formula. They're really useful. So we'll look at that. And then you should remember also your equilibrium constant and Le Chatelier's principle from last year. We'll go over it all again though. So these are some ions you need to know. For level 3, you should know pretty much all of these, plus more, like I put chromate there, not dichromate. It is a lot, particularly if you haven't been, doing chemistry recently or so on. So there are different tips. I've got your Homer Simpson eating a donut, so ate a donut. Think of the O for oxygen. So if something ends in 8, it has oxygen in it. Okay, so there's carbonate, hydrogen carbonate. Okay, what I've also highlighted here is point number 3. If you add a hydrogen to an ion, the charge decreases by a +1. So if you've got carbonate, a CO3 2 minus, then hydrogen carbonate has got 1 less negative charge because you've added a +1. So it's HCO3 minus. So you've got your sulfate, hydrogen sulfate, phosphate, hydrogen phosphate. So if you know the one like carbonate, sulfate, phosphate, then you should be able to work out the other ones, hydrogen phosphate, hydrogen sulfate, hydrogen carbonate. To remember the 8 compounds, sulfate, carbonate, phosphate, chlorate. I haven't included chromate in my little thing here, but one way you could remember it is school chef cooks next pancake, where the vowels is the charge. So if it's got 2 vowels in it, like school, it's got a charge of -2. And then the consonants are the number of oxygen atoms. So school, it's got 4 consonants, so it's got 4 oxygens. The S for the sulfur, so school stands for sulfate. Chef, chlorate. Cooks, carbonate. Next, nitrate. Pancake, phosphate. Might be a way. Do you remember these ions? Do you know these ions off by heart? Some. Okay. It is good to know because you may be given it in the exam somewhere, but you certainly wouldn't be given everyone. You would be given perhaps formulae, but you need to be able to divide them up into the ions. And then once you've worked out the 8 compounds, you can work out the hydrogen 8 compounds like hydrogen carbonate, and then the 8 compounds is always one less than an 8. So sulfate has got 4 oxygen atoms, sulfite has got 3 oxygen atoms. Nitrate, 3 oxygen atoms, nitrite, 2 oxygen atoms. So it's not very clear because of that blue thing coming over it. So please make sure you learn those. Some of them, like permanganate, you've just got to learn off by heart. Chromate, you've just got to learn off by heart. Okay. So let's, if you've got a paper handy, in fact, it would be quite good if you had a calculator, even if it's your computer calculator, and a pen and paper handy in this lesson. So do you have them ready, or do you have them available? Okay, great, because once we get to the calculations, I want you to try it out. Okay, so yeah, Catherine, you can get one if you like while we're doing this. What I just want you to think of is, can you recognize the ions in all of these? So this is silver chromate, the one that we mentioned earlier on. So do you know where to break it up? So between the silver and the chromate, it's not there and between the Cr and O, it's just simply between the silver and the chromate, and you'll get the silver ions and the chromate ions. I haven't done it stoichiometrically at all, I'm just breaking it up. KCl, I hope you can recognize that you're going to get a potassium ion. Now you must make sure your charges are correct. At level 3, everything must be perfect in terms of charge. You should actually also in equations put your states in as well at level 3. So is it aqueous, is it a solid, and so on. Sodium hydrogen carbonate. Can you break that one up into its ions? So I can just see you typing. If later on, if anybody's watching the recording, you can just work it out. Right, Na+, great, and HCO3-, correct charges and everything. So there you go. Calcium sulfate, you break it up between the calcium ion and the sulfate ion. And so there it is, and it is a Ca2+, and a sulfate is 2-. This is ammonium nitrate. It's broken up between the ammonium ion and the nitrate. So there you go, the copper carbonate, Cu2+ and carbonate, and the magnesium hydroxide. If it's got brackets, it's actually quite a bit easier because it's everything inside the brackets will be an ion or a cation. So that's an OH. You just got to know it's OH-. So do you think, you might have to just revise a bit, but do you think you would be able to, once you know your ions, break them up into the component ions? So if I give you a compound, you can recognize the component ions. Yep, okay. So that is really an important skill for this task, for the exam. This sort of diagram came up in CH3001, which hopefully you did ages ago. It's on page 39 if you want to look at it again. It's to help you with your solubility rules. Now, the general trend is that the smaller the charge, the more easily that ion will dissolve in water. Because can you imagine if you've got a 2+ charge or 2 negative charge, it's got a much stronger attraction to the ion. The electrostatic attraction is stronger, so the water molecules have to work harder, give off more energy to try and dissolve that ion. So what you'll find is group 1, because it's only got a charge of +1, are soluble. I've just focused on the elements you'd come across. Hydrogen, of course, is soluble as an ion. So I should have included that. And lithium generally can be soluble too. But certainly the ones, the sodium and the potassium, are definitely always soluble. So group 1, ammonium salts. So remember with ammonium nitrate, any ammonium salt, it's always soluble. So those are cations. And any nitrate is soluble. Any nitrate and actually any ethanoate or acetate is also soluble. You could perhaps remember this as, I put the GR underlined, GRAN is gran. Okay, so gran is soluble. So that's one way of remembering it. The halides, which is -1, so again, remember I said the smaller the charge, the more likely it'll dissolve. They tend to be just about all soluble, but there are exceptions. So what's highlighted in green here, it's your silver chlorides and silver bromides, silver iodides, okay, that are insoluble. Your mercury ones and your lead chloride, lead bromide, they tend to be, they are insoluble. Okay, but otherwise they are soluble. So that was your chlorides. If we move in to group 2 or group 18, sorry, not 18, 16 over here, then they start getting to be more insoluble. So magnesium has some soluble salts, but tends to be fairly insoluble, and certainly your calcium, strontium, barium tend to be quite insoluble. Okay, and a lot of magnesium salts are also insoluble, and you'll find the same thing with your oxides, your sulfides, they tend to be insoluble. So sodium oxide will be soluble because of all sodium salts are soluble, but if I had calcium oxide, it's coming in over here, it'll be insoluble. And if I had aluminium oxide, it'll be insoluble. Aluminium salts being Al3+, do you think it'll be very soluble or pretty much insoluble? Insoluble, yep, because of the charge of +3, it's just about every aluminium salt's insoluble. So there you go, oxides, sulfides, because they're in group 16, insoluble. Hydroxides, although it's only a charge of -1, it's actually because they're so small, they tend to be insoluble. There's a lot of stuff involved exactly why something is soluble or insoluble. I'm just giving a broad brush thing. Carbonates tend to be insoluble. Obviously group 1 and ammonium carbonates, hydroxides, sulfides and oxides are soluble because of that, but otherwise anything else is insoluble. And the other one that sits sort of in between is the sulfates. Sulfates are quite big and bulky and so on, and so quite a few sulfates are soluble because it's just so big. The solid, when you've got an ion like calcium, perhaps that's not a good one, calcium sulfate, but the calcium sulfate's sort of on the borderline between, it's not very soluble. But magnesium sulfate, for instance, is soluble because the magnesium ion is quite small, the sulfate is very big, and there's just that bit of distortion, so it dissolves more easily. So sulfates sort of sit in the middle between soluble and insoluble. Any questions on ions or solubility? No. Okay. So you know if a nitrate like silver nitrate is added to a solution, you know that any nitrate salt that you form will always be soluble. So you never focus on the nitrate, you focus on, say, if silver nitrate was added to a sodium chloride solution, you should know that all sodium salts are soluble, all nitrate salts are soluble. So it's the silver and the chloride that's going to precipitate, so that is going to be the salt you're going to focus on. Okay, the next point, remember, was the calculations from previous years. So you should know how to calculate the amount in moles with the mass divided by molar mass. So learn your units as well, because your units, can you see the G on top will cancel out the G underneath it, and the per mole at the bottom becomes mole at the top. use units to help you work out what is, whether you divide or multiply or so on. So if you don't know where to start, play around with the units to see if it comes to something recognizable that you can recognize. So concentration is the amount in mole divided by the volume in liters. So if you are given milliliters, you must convert milliliters to liters. That's really important, otherwise you're going to go wrong, because this is moles per liter, it's not moles per milliliter. So remember, moles per liter must be the same thing on this side, moles per liter. And then this is a new one, which you may not have come across, but it's just combining those two. It's when we have concentration in grams per liter, because that you could be given grams per liter, because you're expected to be able to work out moles if you're given grams. So if a concentration is in grams per liter, then it's just simply the mass in grams instead of the amount divided by the volume. So can you see how the units help to work out what formula you use? If it's grams per liter, I've got to have mass on top and volume at the bottom, because it's grams over liters. So do you think you'd be able to work that out? You'd be okay with that? Okay, great. Right, what I'm going to show here, this is from Visichem. It's to look at what is happening when something dissolves, because when you sort of know what's happening when something dissolves on the particle level, it sort of makes more sense. So basically it's showing a solid sodium chloride, so it's showing the lattice, so you're looking at the 3D lattice, and notice those bonds aren't fixed and rigid. The whole thing is vibrating and moving. Now when you're adding water, it goes immediately to the most exposed place, because that's got fewer attractions, ionic attractions. And can you see how the chloride's being surrounded by the hydrogens of the water? And there's a sodium now. It's still going on the corners because it's got the least attractions. And it's that competition between the water molecules. Okay, I'll just go back a bit. I'll just move it over there. And there's that competition between the ion dipoles being formed between the water and the ion, and the ionic bonds being formed, the ionic bonds between the sodium and the chloride. So it's a sort of tug of war all the time. And when there's enough energy, that will then be pulled out into solution. And that is how something dissolves. If I go to the next one, this is showing when a substance is in solution already. So can you see, here's my chloride ion, this green one, and can you see how my water molecules have actually surrounded it? What is closest to that green negative ion? Is it the hydrogens of the water molecule, or which is white, or the red oxygens? What's trying to surround it? It's the hydrogens, okay, the white ones, they're sort of closest. So this is sort of showing what's happening. Remember, everything's moving around. Every ion is hydrated, so can you see that hydration around there? Okay, there's my chloride ion, and hopefully a silver one's going to come up soon. Okay, there's a silver one, and do you notice the chlorides and the silver, there wasn't silver, there was actually sodium, but they can meet up, and because of the strong attraction to the water molecules, they can bounce apart. But they can meet up, they could precipitate, depending on the energy, if it's strong enough, or they'll just go back into solution. So if I just go back there again, whoops, over there, trying to see when they met up, yeah. So they could precipitate here, and thinking of solubility, equilibria that we'll be going into, that because they're moving, it could precipitate or it could go back into solution. So have you got an idea on the particle level what is happening when we put a solid into water? So you've got your ions, they've been had a tug of war, taken apart, normally from the corners of, or any jagged ends of the crystal, and it gets dissolved in, and then these ions move around constantly and they can bounce off each other, or they could precipitate out. You wouldn't have to describe anything like that, but it does help if you've got that idea. Okay, what I want to go on to next, from being able to break up the ions, we need to work out how many particles would go in solution. We saw those sodium and chloride ions going to solution, and that's an example of an AB salt, which is for every sodium ion there's a chloride ion. So if my sodium chloride dissolves, if I've got S amount or S concentration of sodium ions, I must have S concentration. S just for solubility, that's why I chose S. You can make it any figure, any letter you like. But you'll have to have exactly the same for chloride. So if my AB molecule or ionic compound breaks up, I've got exactly equal amounts of A and B. Is that clear? Okay. Now, notice I've said here, and neither of the ions reacts further with water. That's going to be important in the next lesson, but not in this lesson. So we're just assuming my sodium and chloride, they're breaking apart. Yes, the sodium ions are being surrounded by water molecules, so my chloride ions, but they're actually not reacting with it and changing something. Okay, if I've got an A2B salt, so this would be like the silver chromate that I was speaking about earlier, or what you saw earlier, Ag2CrO4. Then if I break it up, I'm going to get twice as many silver ions in solution to chromate ions in solution. Or if I had something like magnesium chloride, I'm going to have 1 magnesium to 2 chlorides. So 1 magnesium to 2 chlorides. So that's why it's so important that you know how to break up ions, so you can work out what the relative amount is. So here's another example. I've got calcium sulfate. 1 calcium sulfate, so if I was talking about the solubility of calcium sulfate, it's because I've got 1 calcium being formed, sorry, I've gone to click too fast, and 1 sulfate. If I had silver sulfate, I'm going to have 2 silvers to 1 sulfate, and if I had calcium chloride, I'll have 1 calcium to 2 chlorides. So what I've got here now is how we're going to use that in this next section to work out your equilibrium constant. What do you remember about an equilibrium constant from last year? Do you remember anything? Not really. Okay. So we're going to be looking at sparingly soluble salts, so the salts that don't dissolve easily. They're pretty much insoluble. But just to look at what an equilibrium constant is, my ions in solution are, if they're in equilibrium, and that's what we mean by those arrows over there, a half arrow forward and a half arrow back, it means my rate of dissolving, my forward rate, is the same as my back rate. So for every calcium sulfate that dissolves to form 1 calcium and 1 sulfate ion, somewhere along the line in the solution, 1 calcium and 1 sulfate will collide and form a precipitate again. So I've got an equal forward rate to equal back rate. So that's what we mean by equilibrium. So my equilibrium constant is something that describes the concentration of your products multiplied together in a ratio to your reactants multiplied together. And it's only changed by temperature. So if I change my concentration, it doesn't affect my equilibrium constant. My equilibrium constant is a constant value. You can look up tables upon tables of chemical data books. That equilibrium constant is constant for particular temperatures. So the one that's normally quoted is always the one at standard temperature, which is 25 degrees. So if we given a value, or you'll notice in the exam question, they'll say at 25 degrees. It's just because the constant depends on temperature. So if I have my concentration of calcium with my concentration of sulfate goes on top, and I divide it by my concentration of my reactants below here. Okay, oh, I forgot to mention, when I take an insoluble salt like calcium sulfate, it's not particularly soluble, I get a saturated solution quite quickly, where it means no more solid will dissolve. So it's, say I've got a beaker of water, I've added calcium sulfate, as much as can dissolve will be dissolved, and the rest will stay undissolved. So my substances, my ions in the solution is in equilibrium with my undissolved calcium sulfate. That's my saturated solution. Right, so if I'm looking at my calcium ions and sulfate ions, and I'm multiplying their concentrations together, and I'm dividing it by the reactants, what can I say about the K value? So if I've got a big K value here, what can you tell me about the products? Have I got more products or less products? In other words, is the equilibrium lying very much to the right, so I'm getting more products if my K is big? Okay, more, correct. So if that's big, I've got to have a big numerator, so I've got more products. If K is small, I've got to have a big denominator, which means I've got more reactants. So the bigger the K value, the more products, and the further the equilibrium lies to the right. Okay, or the more the equilibrium lies to the right. And I can't spell equilibrium, sorry about that. Right, so we've looked at just general equilibrium constant. Now we want to look at this, what we call the solubility product. Can you see it's Ks? I've shown Kc. Kc is just for concentration. Okay, that's where that C comes from. Now I want to look at S. That's from solubility. So what we've got here is the products, calcium and sulfate ions, and we've got a concentration with those. But can I have a concentration of a solid? Does the concentration change of a solid? No, it doesn't. It's a constant. You know, in a crystal, those ions, they're a certain size. They can't get packed closer or watched together. So what happens here, that this constant, because it's a constant concentration of a solid, that simply gets put as part of the equilibrium constant value. So I've got two constants multiplied together, and those two constants multiplied together give me the Ks value. So a Ks only has the numerator. There's no denominator. Can you see it's missing here? If both of these were in solution, I'd have reactants, but I don't. So I've only got the products multiplied together. So if I wanted to do the equilibrium constant expression for calcium sulfate, so there's my Ks now, and it's calcium ions multiplied by sulfate ions. Now notice the sort of brackets I'm using. They're square brackets. What do square brackets mean? Okay, I see Catherine's typing. Square brackets are used in a number of different places in chemistry. Okay, absolute value, they may, I'm not too sure about that, Catherine. It just simply means, in this case, it means concentration. So you'll notice sometimes in my calculations, I'm changing from square brackets to the normal round brackets. And it's because in round brackets, I use numbers. When I have square brackets, it means concentration of. You've come across square brackets in chemistry with Lewis diagrams, Lewis structures. Remember when you had to draw a Lewis structure of an ion, you had to put in square brackets. Okay, I know there's another place you use square brackets. It's used in different places in chemistry, and this is one of them. So what I want to point out here is that Ks is equal to the concentration of calcium ions in square brackets, because that's what concentration means, multiplied by the sulfate concentration. This whole thing over here is called the solubility product expression. So when you're told to write the solubility product expression, then this is the sort of thing you write. You take the products, you put them in concentration square brackets, and you multiply them together. And then this over here is the value. And as I say, this has been measured for 25 degrees. It's been measured at a lot of different temperatures, but the standard one is always at 25 degrees. And this is a fixed thing. Okay, the only thing that will change this value is the temperature. Okay, and there it is. Right, and there I'm highlighting, and it's the square bracket, sorry, I should have pointed out, also means in moles per liter. So that's just the convention we use in chemistry. Right, so if we've got an AB salt, my AB breaks up into AB ions. Now it could have been A plus and B minus, or could have been A2 plus and B2 minus. It does, you know, depends on the ion. So my expression will be the ions multiplied together. If I have an A2B salt, I've got twice the amount of A. So if I do that, can you see it's A times B? I've got to multiply all my products together. I can't just say A times B. I've got to go A times A because I've got twice the amount of A. So A times B, and so what it ends up is A squared times B. Okay, and if I had the AB2 salt, it's A times B, so it's the same as the concentration of A2 plus times the concentration of B minus squared. So what I want to do is classify these salts, and then we're going to write the equilibrium constant expressions, see if we can do it. So I don't want to, see we're halfway through the lesson, so I don't want to take too long. So I hope you can recognize this as being a A2B salt, and I've given the ions there. So if this was a recording, you would stop it and try it out yourself, but I just want to move through. So there's your Al, so aluminium phosphate is an AB, sodium dihydrogen phosphate, because I've got two hydrogens there. Remember, for every hydrogen you add on, you drop in charge. So this is just, phosphate was PO4 3 minus. I've added two hydrogens, so it's H2PO4 minus. Barium sulfate AB, ammonium dichromate A2B, lead chloride AB2, copper hydroxide AB2. Hopefully you would have been able to do that. Do you think you would? Yep, great. So now we're going to do exactly the same thing, but now we're going to write the expression. So now you've got to think of, where do I square it? Okay, so let's do this one. It was an A2B salt, so I've got twice the amount of silver, so I square it, because it's silver times chromate, so it's silver squared chromate. Okay, that was an AB, so it's just a straightforward multiplication. That's an AB, that's an AB. This is an A2B, so I've got twice the amount of ammonium. So it's ammonium times dichromate. So it's ammonium squared dichromate. This is an AB2, so it's lead times chloride. So it's lead chloride squared. And copper is for copper hydroxide squared. Do you think you can write the solubility product expressions? Good. Okay, because this is how you always start these problems. Well, it's the second step when we do these. But what I want to do here very quickly is look at this. So what I've got here is if I'm going to go, this is the FET one. It also comes up in the book, and I'm going to choose, well, we can do mercury bromide. That's an, let me go for an AB salt, so silver bromide. If I shake this, okay, you're going to see it's going to dissolve. Can you see it's sort of all dissolved? And can you see it's in equilibrium, getting dissolved, it's coming out as a solid, but it's going back in again. In fact, it's now become a saturated solution because I've got a little bit of undissolved. Bound means undissolved. Okay, and can you see I've got the same amount of A as well as B ions in solution. If I add more, then you can see those numbers stay pretty much the same. Okay, they're always around about 44, 45, round about there. I'm just getting more undissolved. And if I add more, then that still stays round about the same, but I'm getting ions constantly going off and adding back on again. Have a look also at how much is here. I don't have, okay, this just gives me the amount. Okay, I thought it might give me the E naught value. If I go to, so not E naught value, I was talking about the K's value. If I go to, say, mercury bromide, okay, so it's starting to dissolve. Now, can you see there's a different ratio there? Okay, yep. So you can play around with this. It's just to get you an idea, because if you sort of know what's happening, I think it's easier to do the calculation because you can visualize it. This design a salt, right, this is what I wanted, is when you go to design a salt, you can change your solubility product. Remember your K, they say KSP here, that's New Zealand, we just say KS. In America it's KSP, but can you see it's really for K solubility product. That's where the SP comes from there. Just add a P, but otherwise it's the same thing. Now, this is a ratio of 1:1, cation to anion. So if I have a KSP of 1, we'll just keep it to that, and I dissolve, what I really want you to look at is the amount of substance that will dissolve compared to the value. So you can see I've got now a solid, it's a saturated solution. If I change my cation to a +2 and I do the same thing, can you see for my same KSP value, it looks as though a lot more can dissolve? Can you see it looks a lot more crowded? So what I'm trying to show is you can't compare KSP values, or KS values actually, for salts with different ratios. So I can't say the KS for silver chloride is 10 to the -10, and the salt for calcium chloride, that's now a different type of ratio. One was AB, this is now a AB2 salt, is 10 to the -12. Which one is more soluble? Can you see you can't do that because they're different ratios? Because here you can see dissolving a lot more. The only way I can compare KS values is if I do it for the same ratio. So here's one with 2:1, okay, and you can see it's still dissolving. I've got, okay, it's because I've added now, but can you see it's still saturated? Whereas if I now make this, I've changed my KSP Can you see how suddenly I've got a whole lot of things precipitating out? So with the same ratio, you can compare, but you can't compare with a different, AB, AB2, that sort of ratio. Okay, so I'm going to go back to my PowerPoint again, and right, so that's all what I wanted to show with that. Okay, now let's do the calculations. I've got the eek method, so when you see a calculation, you can go eek. Okay. But if you follow this method, this will really help you minimize your mistakes. The first thing is you write your equation, because if you get your equation wrong, your expression will be wrong. And sometimes you think you can skip the equation because you know the expression because it's so obvious, but then you do something, make a silly mistake. So write always your equation first. So if you've got silver chloride and you want to write solubility equilibria of silver chloride, you'll write down AgCl in equilibrium with Ag plus and Cl minus. Yes, include the charges. Particularly with the expressions, it'll be marked wrong if you might have everything in the right ratio, but if you don't have the charges correct, it's wrong. So the next thing you do is the expression, and only then do you start your calculation. So as I said, by writing a balanced equation first, you just start minimizing errors. And what I've got here is this, the REQ is before EX, which is before K. So it's in alphabetical order, so you know you write the equation before your expression. And I think that's quite obvious anyway. Oh, that should have come up next. Always double check your calculations, especially when you do square roots and or cube something or take a cube root. You can often press the wrong button in your calculator, so always recheck your calculations from the beginning. And then, as I say, make sure you do the expression correct, because the expression will tell you whether you square something or don't square something. Okay, now there are 4 calculations you can get, and we'll only do the first 2 in these lessons. These first 2 are pretty much an achieve level question, although you can make it harder to get a merit or excellence out of it, but otherwise these are pretty straightforward, number 1 and 2. Calculate the solubility product, the Ks value. If you do that, your answer has no unit, and you will be given at least 1 concentration. Okay, the only way they can make this a bit more difficult is if they give you a mass and a volume, so you've got to then work out the number of moles and then the concentration. In other words, they don't give you the concentration because they've given you a mass and a volume, and then you have to work it out. The other one is doing the reverse of the solubility product calculation, is calculating the solubility. So here it's the reverse, so they give you the Ks. And because you're calculating how soluble something is, you do have a unit, which is the moles per liter. Okay, and then number 3 and 4 will happen in the next lesson. Okay, so let's calculate the solubility product. So here's an example, the solubility of CaF2 in pure water. Now, this is important at pure water in that there's no other source of calcium and fluoride ions. So we're assuming, or we know because it's pure water, all the calcium we've got is from the calcium fluoride, and all the fluoride we've got is from the calcium fluoride. There's no extra in the tap water or anything like that. So that's the reason why we say in pure water. So we know all the calcium fluoride, all those ions comes from what I'm adding. So we get given that solubility, so we know that's how much will dissolve. Okay, so now I've got to calculate the solubility product. So the eq rule is, remember, the equation first. So write your CaF2, and that will help you work out whether I have to square something in my expression. So if you do that, you can easily now go, oh, I've got twice the amount of fluoride, so I've got to square it. Now we do the calculation, because we now have to substitute values in there. So what we have to do is we say, okay, calcium fluoride. For every 1 calcium fluoride, I get 1 calcium ion. So if I know the solubility of calcium fluoride is that, it's going to be the same for my calcium. Can you see there 1 is 1, So I have got 2.31 times 10 to the minus 4 is the same as that. Is that clear how we get the calcium concentration? Okay. The fluoride, okay, is twice that. So I've got to multiply that 2.31. I can't use that same one. Okay, so I have to multiply it and I get 4.62 times 10 to the minus 4. Okay. Yeah. Yeah, it's all on stoichiometry and so on now, yes. So now I'm going to, I've rewritten it down because now I want to do my calculation, my substitution. So that value gets put into there, okay, that green value gets put into there. Now, do you notice what I did to the fluoride? I've doubled it here, and now I'm going to square it as well. So when I've got an AB2 or an A2B, I have to double and square when I do a straightforward solubility product one. Okay. And so there is where I've squared it, because can you see I've taken the 2 away. I've already squared it. And you know what I was saying about the square brackets and the round brackets? I should have put round brackets here. So those should have all been round brackets, because they're valid there, but these are straightforward numbers. Okay, now just multiply those two together, and I get that. Now make sure you use your sense to see if it's a sensible answer. If I've got exponentials of minus 4 times minus 7, remember they're additive. So negative 4 plus negative 7 is negative 11. So I must get an answer of round about negative 11. If I got an answer of negative 21 or positive 11 or something like that, you know you've made a mistake. So check that you haven't done a silly error like you've forgotten to square. If you get something like negative 8 because you've done negative 4 times plus that negative 4 is negative 8, you know you've forgotten to square. So always check to see if your answer is sensible. And then remember, a Ks value, there is no unit, not as far as level 3 chemistry is concerned. You'll be taught something a bit different at university. Any questions on calculating a solubility product? Nope. Okay. Right. Now there's a shortcut. For the straightforward ones, okay, where it's in pure water, you can just use a shortcut. Because if I said for every AB2, I get one AB, so make that S for solubility, but I get 2 of those, so it's 2S, and I've got to square that 2S. Can you see I'm going to land up with this little formula? Ks is equal to 4S cubed. So if you just remember that one, you could just substitute into there. But don't forget your equation and don't forget your expression first. Remember the eq rule. Do those first, because otherwise you might not recognize it's an AB2. Okay, the same thing for an A2B. It's the same sort of thing. We'll land up with the 4S cubed. And with an AB salt, it's just a straightforward S squared. So if I wanted to calculate the Ks, you just put in the solubility in there, cube it, times it by 4, and then you get the answer. The same thing for this. Here you just take the solubility, square it, and you get the answer. If it was going the inverse, you would just do the opposite, but we'll get to that. So here's the same problem we did, but the shortcut method. So remember that we still do the eq part. Now we're just going to put this equation down. Ks is 4S cubed because it's an AB2 salt. And now we know S is that. So we just cube 2.31 times 10 to the minus 4. That comes from there. Multiplied by 4. Now remember, we multiplied by 4 after we've cubed it. A common error is you take this 2.31, etc., multiply it by 4, and then you cube it. Can you see you're not going to get the right answer? So always check. And as I say, if we did it, we should get the same answer as we did before. And again, if we raising to a power, minus 4 is now times 3. You'll get minus 12, and this is close enough to minus 12. So that's a quick check to see, is my answer sensible? Right, so let's go. I see the time is going on. We've got 2 minutes left. Here's another example. So I've been given the solubility. These are pure water coming up again. Calculate the solubility product. So here we go. Do that break up into ions. Recognize it's an AB one. So for every 1 barium, I get 1 carbonate. So the solubility is the same. Oh, that should not have been in there. Please ignore that. Okay, so Ks is just simply those two multiplied, and there you get an answer. Remember, no unit. If I did the shortcut, I would just simply square that and I'd get the same answer. So hopefully, just as I say, ignore that bit over there. You can see they're fairly straightforward. The hardest part to me is actually working out this bit over here. So if you've got that right and you know how to use your calculator, everything falls in. Here's another one where it's an AB2. So you're given a solubility again. Right, you've got to calculate the solubility product. You've got 2 hydroxides now. And so we've got a squared. So when we've got this, remember you double and square, or you use the 4s cubed. So we'll do that shortcut in there. So there we've got that. And now we just put that in. Can you see this has been doubled? And we're going to double and square it. And we get an answer of that. Okay, the shortcut is just simply cube the 1.01 times 10 to the minus 5 multiplied by 4. Okay, you can see there I've cubed it, multiplied it by 4, and I should get the same answer. Any questions on calculating the solubility product if you were given a solubility? Nope. Okay. Now we're going to calculate the solubility. So here you get given a solubility product. Okay. Now calculate the solubility in water. So notice that's a solubility product. There's different ways you can recognize it. The easy one is there's no unit. If you say you were skim reading and you didn't see the word product, you just saw the solubility of, the very fact that there's no unit there means it can't be a solubility, it's a solubility product. Another sort of giveaway, it tends to be quite a small number, but you can get, say, 10 to the minus 6 as well, which is often the same as a solubility. So just be aware of that. Right, so here we calculated. Remember, first of all, the eq part, equation, expression, see which one we have to square. Now, the easiest way to do is let silver be 2s and chromate be s. That's to use the shortcut rule. Okay. Well, I've done that thing there again there, but otherwise you do the same thing. And now I've substituted my Ks value, 9.10 times 10 to the minus 12. It's been put in there. Now, I'm trying to solve for S, so to get rid of the 4 on the right-hand side, because I want it away from the S, because I'm trying to solve for S, you divide both sides of the equation by 4, because remember it's equation, so what do you do to one side, you do to the other side. So 4 divided by 4 is 1, which gets rid of it on this side, but over here, if I divide by 4, it stays. Now, I suggest you always calculate this bit first, before you try and take a cube root. Okay, so can you see I've changed that? 9.1 times 10 to the minus 12 divided by 4 comes to this value over here. Okay, and I use sense. 9 divided by 4 is round about 2. Okay, and now I take the cube root. Make sure you know how to use your calculator to get a cube root. Play around, in the book I've given a tip, can you get 2 cubed is equal to 8 and 8 cubed root is equal to 2. Play around with the calculator if you can get that right. And there's your answer, and notice the unit. There is a unit, and also please, for excellence, you need to get the correct number of significant figures. And it should always be 3 pretty much. Okay. And then again, is your answer sensible? If you're taking a cube root of 12, 12 divided by 3 is around about 4. So negative 12, negative 4. Just do double checks. Have I made a careless mistake? Here's another one from last year's exam. So this is, say this is an achieved level question. So you've got to calculate the solubility of lead chloride. Now they want you just not just to have the lead chloride solubility, but they want you to have the lead ions and the chloride ions, because they want you to see that there are twice as many chloride ions. So that's why the expression is, or the equation first and then the expression is so important. You've got twice the amount of chloride. So start with those. And now we just do the same sort of thing. Find S. But we're not finished, because all what we've done is that bit over there. So we haven't done the and give the lead ion concentration and the chloride ion concentration. Now this is directly out. So do you see how square brackets means concentration? You need to know square brackets is concentration. So we've got the solubility of lead chloride. For excellence, write a statement like that, because you asked for that. And now we say, okay, one lead chloride gives one lead ion, so it's the same, but one lead chloride gives two chlorides, so it's, can you see that's double? Any questions? Nope. Okay, and there again, sig figs and units. Here's now from the year of previous year's exam, 2013, and so we get given now a mass, so they've made this a bit more difficult. They've been given a mass and a volume. You weren't given a concentration in moles per liter. And then you're given a molar mass. If you're not given a molar mass, you're always given a periodic table, and you go to the periodic table and you work out the molar mass. So don't think, oh, I don't have the molar mass, so I can't do it. You can work it out. So again, calculate the solubility. And so the same thing as you'd had to do for last year, give the silver and the chromate ion concentration. So start off equation, expression. You'll make less errors. So you do the same thing. I've got twice as many silver ions. Okay, and as I said here now, I don't then give me the KS, so I can't now substitute in there and work out my S. So you have to now work out what you do know, and that's what we know, those three things. So there they're repeated. So we've got to think of what formula do we know? Well, we know N is equal to small m over big M, moles is mass over molar mass. So I can work out my moles of silver chromate, and use units to make sure you do the right thing, multiply or divide. So if you weren't sure what your formula was, use the units. Now that I've got my amount in moles, I can work out my concentration. Okay, and can you see I've now worked out my solubility and can you see I've worked out my solubility without actually using my KS value. So start off like that, but then you realize, oh, I've gone wrong. Well, not wrong, but I've got to do another method. So I'll go into the next slide now. So we've got the solubility of the silver chromate. Now we've still got to do those two, the silver and the chromate. So remember, one silver chromate is one chromate, and it's two silvers, so I get double the amount of silvers, but the same amount for chromate. So we've done part A. Now we actually have to calculate KS based on the solubility we worked out. So we've got about a minute left. That's your answer sensible. Always check that. So here we just work it out using the same method we did earlier when we were calculating solubility product. That's 4s cubed, and so we just work it out. And here's another, the longer method, where we just take those values. Okay, the silver is 1.7, and remember we've got to cube it. We don't double it in here because we've already doubled it over there. Right, and there's your dichromate, and Can you see we have a slightly different answer? And the reason for that is here I used all the figures in my calculator all the way through. Here, I just actually rounded them off. I used the 1.73 and the 8.67. I didn't use all the other numbers that came with it. And that gives me a slight difference in the answer. If I'd kept all my figures, I would have got exactly the same answer. Okay, then finally as a summary, okay, what we did this time was substances in pure water, no other sources of ions present, and because of that we can use these shortcut equations. Okay, so S is simply the square root, or if for an AB or A2B, it's the cube root divided by 4. And then what I've got here, and it's also on page 25, it's the difference between solubility and solubility product, which is sometimes useful just to go over. Any questions? Nope. Okay. Did I go too fast? Do you think you've understood those two types of calculations? Right, great. Okay, because if you get those, those would be achieved level, or when they throw in a bit of the mass and the so on, that would start going up to merit level. For excellence, you'll be doing the more complicated ones, and that's what we'll do in the next lesson. So, see you next week. Right, bye.